I'm really happy to have Sasha Razborov give the first talk today. I've heard it before and it's beautiful. So you speakers today hardly need any introduction, but just to mention one of the many things Sasha Razborov is famous for, being one of the few people who proved lower bounds, original lower bounds for monotone circuits. He had done beautiful work in bounded arithmetic and proof complexity. In bounded arithmetic, last Wednesday we talked about RSUV isomorphism, for example. And he's also well known for probably the most important barrier result in circuit complexity and also in bounded arithmetic, the natural proof barrier. And hopefully you might hear a bit about it today. In addition to that, done some quantum complexity, communication complexity, some other complexity, and some deep mathematics, flag algebras stuff. He unsurprisingly got numerous prizes for that. Just to mention the Gödel Prize for the barrier results for natural proofs, and I think Ivan Lina's prize for circuit lower bounds. There is way too much to say, but I'd rather let him speak for himself. So please, the floor is yours.
All right, thank you very much, Tonya, for the nice introduction. Again, if you want to ask questions, please unmute yourself and ask, highly preferred method. So, and first of all, this talk today will be highly speculative. And it is, I apologize that it's about somewhat old stuff. I will talk here at Simon's, virtual talk somewhere in May on more modern things. And another apology I already made is that some of you or many of you have seen this talk before, a longer version of it, but I still hope I made a few changes. All right, so we start with our favorite problem, P versus NP. I think at this point in the game, everyone here knows what it is, but we are going to tweak this question a bit. So the first version we may ask, and that's how it was attacked. People try to attack it in this form. It's a slightly stronger version, and it's asking whether languages in NP have polynomial size circuits. Let me remind you that P/poly is anything, or is non-uniform P, which means everything you can compute where it's polynomial size circuits. So then we can further relax this question and ask, are there any explicit Boolean functions not in P/poly, with explicit being in good old sense, in mathematical sense, not necessarily NP, or something which you would recognize as explicit? And so then we may ask this question, which looks ridiculous, but as we will see, it is not, at least for the purposes of my talk today. And this question is, actually even more relaxed version. Are there any Boolean functions that cannot be computed by polynomial size circuits? Well, of course, I have put here a question mark. But of course, we all know that it is the case. It's classical result by Shannon, somewhat clarified by Lupanov later. And it says that it is indeed the case, and we have functions, and actually almost all functions are hard. So here is some notation. C of Fn is the circuit size of my function f in some standard basis. So almost all of them are exponential. Almost all functions are exponential, and that's basically the whole proof. It's a simple application of the Pigeon-Hole Principle, but let's look closer at this proof. So what's really going on is that if you want to run this argument, then you want to be able to count really well. And by really well, I mean you are going to be able to count really large numbers. So you want to count up to double exponential double exponent in the number of variables, because it's the overall number of your Boolean functions, or at least up to this number, but still you have to count really a lot. And that will be the main theme in my talk today, is that actually, the main principle is what you can do depends on how well you can count. Right. So maybe you should use it in K-12 education in classes on arithmetic, but that's really, that will be the dividing line. Everything will depend on what is the maximal number you can see in your arguments, and you can count up to that number. So let me now revisit this question. Are there any Boolean functions not in P/poly? And for the purposes of my talk, first of all, we are going to be interested in proof theory. So we are going to study whether this equation is provable somewhere or not, or using some class of methods. And if there are any logicians here or proof theorists, then we will understand, for the purposes of this talk, we will understand proof theory slightly more broadly. It's not necessarily a first-order theory or propositional theory. It's something that, some class of methods that you can rigorously define. That word we don't compromise on. It must be rigorously defined, but other than that, it can be described by various means, and natural proofs that we will see is one of the examples. So, and let me now put here one of my favorite sentences, because, well, you do algorithms, you do whatever, you prove theorems, and when you cannot do something, then you start to explain others why you are so stupid. And as you see, this principle was not invented by complexity theorists, but still, that's basically what we are going to do in this talk. As I said, it's highly speculative, so let me end. Yes, I forgot to say that it will be one of our guiding principles, is that we will be interested in proof systems, again, broadly understood, for which even that statement is supposed to be hard. So only in those proof systems in which you can first formulate this statement, and second, this blue word any does not make your life any simpler. So proving that NP is not in P/poly is supposed to be more or at least as hard as proving it for any Boolean functions. Let me briefly state a few motivations. Right. So first of all, because mathematicians do it, we know great independence result in mathematical logic, axiom of choice, continuum hypothesis, Gödel's incompleteness theorem, and it's self-explaining that it is interesting. The second motivation, it actually started in the book by Gary Johnson, 79, of 79. As many of you know, in the first chapters, they carefully laid down this principle that the theory of NP completeness is good for many reasons, but one of them is that you can explain to your boss why you cannot do the job. So that's the second reason. The third reason, it is of course because since these problems so far, mathematics never gave up on its problems. It kept solving them, if necessary, for centuries, and as we know, eventually they get solved. So we have to continue, and like in complexity theory, computational complexity theory, I mean, it is the same hope. We are going to focus our research in the right direction by just saying what and why does not work. So it's the ideology that we used in our paper on natural proofs. Of course, as Stephen and me had expected, everyone misused that sentence and took the paper don't do circuit lower bounds, do something else. Well, we cannot do anything about it. It was not our intention. Our intention was just that we showed what does not work, and let's take it from there. And the third, but also fourth, I'm sorry, but also very important, motivation is, of course, about byproducts. So again, that's what complexity theory is about. You prove something totally useless, and then something comes out of it that makes a difference in the real world, even if you did not even think about it. Or the same sort of happens in this business as well. All right, so what's next? So diagonalization, it probably was the first barrier. Let me go over this slide very quickly. So it's a proof system in my sense, right? So if you have a complexity result, then the proof system, it simply says that it should be true in all Oracle worlds. It's well defined. It's not, of course, like the usual proof system, but still it is rigorously defined. And we all know this classical theorem by Baker, Gill, and Salovey is that this proof system is not capable of proving either P is equal to NP or its complement. That's probably the first manifestation. That was probably the first manifestation of this idea that a proof system is not necessarily rules and axioms in first order logic. It might be something else, but something reasonable. So what does it mean to be reasonable? Again, let me try. So 4 will be a magic number for some reasons throughout my talk. Let me formulate 4 constraints and wish lists that I would like to have in a framework that barrier or proof system, whatever you like, to study this kind of things. I mean. So the first, of course, is that your proof system should not be able to solve this question in the obvious way by counting. And it rules out strong proof systems like those. Well, Shai probably will disagree with this, but we will listen to what he can say in an hour about stronger proof systems. So, but for the purpose of my talk, I really don't want Shannon arguments to be formalizable in my proof system because it's not an interesting proof. I want it to be out. So the second, which is very important, is that if you take your favorite result in circuit complexity, and we do have a few results, as you know, and by the way, it is an excellent book, one of the best books I've ever seen. So if you take any result from this book, then you really don't want to work hard on proving it in your system. You don't want to write papers, you don't want to introduce something, some new concepts, you just take it and it should be doable in your system in a straightforward way. So, and returning to my counting theme, turns out that now all those results well, except of course from that book, except of course for the chapter that talks about Shannon counting arguments and Lupanov's improvements. All other results, they use only counting up to polynomial in the number of instances. So little n, of course, stays everywhere for the number of variables, so it is just polynomial in the number of your instances. So all those proofs, they use counting only up to this number, which is single exponential in them. Right. So the third is self-explaining. We really want proof system that people care about. And it is probably the weakest point of natural proofs, because somehow that's what we cooked up. I will show you what we did in several slides. So, but still we have some motivations, but other than that, usually it should be natural. The proof system should be somehow of interest. I cannot quantify it. And of course, the first thing is that we really want to hope to make progress. And in logic, you make progress if usually if meta-mathematics of your proof system, so what you can extract from proofs basically, it somehow matches mathematics. So Gödel's incompleteness theorem, it is meta-mathematics, is formulas that you prove, you encode them, and then it is the same mathematics about integers your proof system is arguing about. And if it looks if it looks abstract to you, then let me point out this recent breakthrough result by Albert and Müller, Albert Atzeris and Müller. They proved something extremely concrete, improved complexity, not only extremely concrete automatizability of resolution, but what has been open for decades, and they really use this self-referring argument. So it's not, if you are interested in concrete things, then you still want to have it. Right here, Shai again probably disagrees with this. We are going to listen to it later. All right, so let me remind you what are natural proofs. And I will be very quick because this talk is about something relevant, but still something else. So these are two pieces of common wisdom. So the first one is that if you want to prove lower bounds for Boolean functions, then you should look at how it looks like, study its properties, and then move it to lower bounds. And the second piece of wisdom, it says that if you want to analyze your proofs, then you should carefully look into them, do a proof system, and blah, blah, blah. So the starting point of natural proofs is that we dismiss both of them. So namely, instead of even trying to understand what our proof looks like, so we are going to think about it, sometimes creatively. Sometimes it's not straightforward, and then we are going to conclude that the same argument can be applied not only to your function of interest, but to a great deal of other functions, which gives rise to the set of Boolean functions Pn to which your argument can be applied in a sense. And that's the only thing we need in our model. So we only look at this set Pn, and then we formalize. So sorry, it should be Pn. So Pn and Cn on this slide are the same. So and then we simply write the properties of this set of functions. First of all, of course, we want it to make sense. And the second two properties, they are debatable, but still that's what happens in all or almost all known proofs. And you really want to understand what you are doing. So, which means that our set Pn must be computable in polynomial time in this quantity, and it must have large density. So once you have a good method, then you really are going to be able to apply it to sufficiently many functions. Usually it is even better than that. Usually it is just almost all functions, but to be on the safe side. So let us check against our 4 items from the wish list. There is no obvious counting solution. You cannot count. That's why we have here constructiveness, right? So if you count up to larger than that number, then it will not be in polynomial time. So that is what we call naturalization. So there are some technicalities with monotone formulas, basically because it is not so easy to define a good distribution over monotone formulas, but more you can do it. So as I said, this is the weak point of natural proofs. So you can prove, but here is at least one justification for it, which is also well known, that it's written here. If you prove that a pen is hard and your proof system is closed under X4, then you somehow, and you understand what you are doing, then you should be able to tell which one of these two is hard, and it gives you largeness because you have then half of all functions. And here, on the 4th item about mathematics versus meta-mathematics, it is almost here because one of our axioms, it has polynomial inside of it, and we study right short circuits, small circuits, but the catch here, of course, is it really a problem that now we have changed our measure, that it's not small n, that it is 2 to the n. Is it really a problem? Well, turns out it is the main and actually the only problem about natural proofs is that you really can prove things even in this form. So that's the main theorem of natural proof. So modular standards, cryptographic assumption, there is no natural proof against general circuits. Self-defeating arguments in its pride. Good. So as I said, there is lots of work on natural proofs, and people disagree with many of these points. Some people agree, some people both agree and disagree at the same time. And let me stop it here. So, and this is one very important byproduct. So it will be the same throughout my whole talk, that we actually are interested in our inputs. We are measuring our main size measure is this capital N. It will always be the same, which is the number of instances in my problem, which means that your Boolean functions are given as truth stable. And one byproduct is that this work with Steven Rudich highlighted the importance of this problem, which these days is called minimum circuit size problem. It is here, it is obvious, it is the set of all truth stables that corresponds to simple functions. And let me just say that there has been a lot of very interesting and wonderful and important research on this problem, and somehow our paper helped to understand its importance and that it is a really good thing to study. So in complexity terms, if we forget about all our motivations, then in complexity terms, natural proofs can be easily formulated in terms of this problem as is written here. Right, so that's it with natural proofs. Let's move on. And so these are the 2 points, I repeat here, the 2 points that natural proofs dismiss. Today, in the remaining of my time today, we are going to still dismiss the first point. As I said, we are interested in proof systems that actually do not distinguish between explicit functions and any functions, but we want to replace the second point with its opposite. So we really want good proof systems in the good old sense of formal theories. And of course, as Antonina already said, there is lots of work about it. So here I really want to say just a bit. So bounded arithmetic is just piano arithmetic where you focus on bounded quantifiers, bounded by terms. So you also have sharply bounded quantifiers, and it is important that it is just a normal first-order theory. No catches, axioms, inference rules. So again, as almost all of you know, S21 is the most important theory in the whole family. There is a hierarchy, there is a family hierarchy. It closely models complexity hierarchy, but I don't have much time today, so I will talk only about S21. And the fourth item in my wish list, it is answered by this fundamental theorem by Sam Bass. It's from his book about bounded arithmetic that basically started this whole subject, is that if you prove something existential in this theorem, and A is simple predicate, then you have then it can be witnessed by polynomial time function. So we see here a polynomial time that corresponds to meta-mathematics of our proof system, and it's the same concept we are going to study. Therefore, it's good news for us. So, sorry, it should be S21 reversed. So now, again, it's a shorter version of the talk. I have to skip many details that I gave before. And but you can formalize the question we are interested in. So here I put sub-exponential function to avoid certain trivialities. And this is the question, whether we can prove the existence of a Boolean function Fn. So right. There is no obvious counting solution because we don't know the answer to this question. We don't know whether it is provable or not. Therefore, there are no counting solutions, obvious counting solutions. This is the second part is also very easy and very natural. So if you look at the same statements, but for restricted circuit models, then you can really do it in this system. It is extremely straightforward. So I did it once, and mostly I focused on the question, are there weaker systems than this, where you can prove all that stuff from Stas's book, and so it is very natural, very simple. So, of course, bounded arithmetic, that's what we love for many good reasons. It's not only because we are able to do this stuff. And now comes an interesting part. So that I will show on the next slide, and it's good that I was able to get to that slide. So, but one clarification is that we cannot hope to get to all the way up to this bounded arithmetic unconditionally. So I, like in natural proofs, I do allow you arbitrary reasonable complexity cryptographic assumptions that are short of NP is not equal to KNP, because that makes the whole game trivial. So again, it's a short version. Let me just mention a competing framework, which is promoted by Jan Rudich. So in this framework, you allow even more restricted counting. You cannot really count up to capital M, but on the other hand, it's no longer simple existential formulas. You allow lots of quantifiers. It's a very interesting framework, connected in many respects to what I'm talking about here, but I don't have time to talk about it. So, and now, again, it should be S to 1. So and now we can reformulate the questions we are interested in terms of propositional proof complexity. Because, again, there is a catch here due to sharply bounded quantifiers, but morally, Sam-Bass theorem almost implies that if you prove this in S2 then there should be some explicit sequence of functions for which you can prove the same thing. And once you have quantifier-free statements or only with sharply bounded quantifiers, then you can translate it to propositional proof complexity, propositional logic. You can express it as a propositional formula, the fact that the function fn is hard. And the size of this formula, again, we use our convention or our main principle that we don't care how we encode it. It's simply given by its truth table. We have enough memory or enough time to just encode it as a truth table and measure everything as a polynomial in terms of the length of this truth table. And now comes the main slide. So we have this square, namely we have proofs in bounded arithmetic, and it shares very popular topic connections between bounded arithmetic and uniform complexity classes, given by various witnessing theorems. Sam-Bass theorem was the first theorem from this family. If you have something in bounded arithmetic, a proof in bounded arithmetic as to 1, then you get something polynomially time computable. So if you have sigma, if you have delta 0 be quantifier-free formulas, then you can translate them through propositional proof systems, and this will give you will just work in much more convenient and more elegant propositional world. For example, S2 again, S2 is different. S2 gets translated to extended Frege. So this is also, this connection is very is standard in computational complexity. So every uniform complexity class, essentially every uniform complexity class, you have associated non-uniform class. So what we really need is the force arrow, right? So you would really expect a force arrow on this picture. I give you a propositional proof. It argues about computational concepts, and you want to extract something computational out of it, and then apply your knowledge like we did in natural proofs, or in this implication, apply our knowledge to get conditional results. And it's embarrassing that we almost cannot do it. And I don't understand why. Right. So let me give you a few definitions. Frege proof systems, resolution, Extended Frege proof system, well, I believe that everyone knows what it is, so I have only less than 10 minutes left. I don't want to spend time here. All right, so the success story, and it is precisely a model case of what we would like to have. Idea is called feasible interpolation. That's precisely what we would love to have. So I give you a special pathology, and it all is applied here, and then you ask, and then you extract from it something computational, which is called feasible interpolation. So you can apply it to several systems of interest, but then turns out that you cannot go very far along these lines because simply feasible interpolation fails for more for stronger systems, for systems that we are really interested in. Well, I mean, we are interested in all those systems, as well as everyone at this workshop already knows by this time, but for different reasons. So here is a byproduct of this. One byproduct of this, it is simply because it is simply one quite amazing thing about proof complexity is that really it is the same phenomenon. Unlike circuit complexity, we really don't know if there are any hard tautologies for Frege or extended Frege proof systems. There is no counting argument here. So in this paper, they tried to come up with some examples, but I guess they indicated themselves that it was not very conclusive, and most of those results were solved, I mean, short proofs in Frege or extended Frege were found later on. The principle is that these systems are really hard. So we really want some arguments that we don't understand ourselves. And at the moment, I have only two, and I think everyone has only two reasonably convincing examples of what might be hard for Frege or extended Frege. The first is random CNFs. It's just because we really don't understand why. If you pick a random CNF, why is it unsatisfiable? You have to count for that, and it's beyond the reach of our system, and it is the second example is coming from this business of proving that NP is not equal, is not NP/poly. It is the second candidate hard topology, and it is again, it is we don't understand it to the extent that we don't even know if it is true or not, which makes it a perfect candidate. So I have only a few minutes left. So let me very briefly say that we have some ad hoc results for, so that's now what we are going to study. We are going to try to understand why this thing is difficult for various propositional proof systems. We have a few unconditional results, and it also does not go quite far. So that's basically the last thing I want to show. And Tonya, do I have 5 minutes?
Sure, why not?
Right?
Please, yes.
Okay, good. So I will try to finish in 5 minutes. So that's one suggestion that is still which may lead anywhere. So improve all the stuff to stronger proof systems. So let me start with reminding you about natural proofs. And the way you prove it is that you construct pseudo-random function generator. If you have an ordinary one-way function, then you get an ordinary pseudo-random bit generator out of it, and you can either construct it using general construction by Mikali, Goldwasser, and Rakov, or you can take, for example, Nissan Wigderson that immediately gives you a conjectural function generator, and this is basically the whole proof. You have to supply a few details. So the idea is to try to understand what it looks or what it might look like in the propositional world. So again, I have a mapping. I have a proof system P. So our idea was that if I give you Nissan-Wigderson generator or any other generator, any other reasonable generator, and I give you identically zero string, right? And I ask you, is it true or not that this string is not in the image of your generator, is not generated by any seed, then it's really impossible to do. So if your generator is reasonable, then you cannot answer this basic question. You cannot really pinpoint any particular string in the image of the generator that is not in the codomain of your generator, that is not in the image. And that's what we take as a definition of our hardness. So the idea is, of course, that we can use, so if I give you any string B, then your proof system does not prove that B is not in the image of DC. So, and the proposal is simply to try to somehow write pseudorandom generators is something that is well studied in computational complexity, and so the proposal is, of course, to search for this missing fourth arrow using maybe at least as inspirations what is known in the computational world. So in a sense, good news is that it extends feasible interpolation. So if you have feasible interpolation for your system, then you basically can do it with a slight twist of your generator. And this is the main conjecture, is that if you take any Nissan-Wigderson generator just for simplicity and for concreteness, and you base it on any function, then it becomes hard for extending Frege proof system. So that was made almost 20 years ago. There has been some work, but not much on it, and it is still wide open. And basically, I would like to, that was the main purpose. One of the main purposes of my talk is to draw attention to this conjecture. So here is what we know. We don't know very much. So we know this conjecture for widths, resolution widths, for polynomial calculus. For even for resolution, it is frustrating because we don't know it for exponentially many output bits, only n squared. And it is a very important work by Jan Rudich, so which is again the same principle. You can iterate these generators as you do in circuit complexity, and for example, for resolution, you can get slightly better. You can get 2 cube, and that's probably the best you can do at the moment. It is the proof system where you can lift this stuff. So pseudorandom generator for this system, well, I hope you know what it is. It is the strongest system for which we know these statements. So, and as I mentioned several times, there are many other suggestions. So the obvious open problem, so it should stay S21. It is just the same YR-SUV isomorphism Tonya mentioned before. So it is the main conjecture. Again, it is connected to model theory somehow. So now we have had several breakthrough results in cutting planes in several last years, but as far as I know, they formally don't imply unconditional hardness of this statement. It would be a great problem, accessible problem, I mean, well, unless I missed something and there is a simple reduction, which I don't see. So proof at least its hardness for cutting planes or sum of squares. As far as I know, it is open. Unconditionally, conditionally, you can apply feasible interpolation. And the same equation for bounded depth Frege. We missed some techniques, basically, random restrictions were not suited very well for the task, but these people, they explained to us that it is much more versatile method than we had thought about it. So again, even for resolution, we have to apply other methods. We don't have pseudo-random generator for resolution that is really in the range we are interested in, and it's very loose because it's very loose creation, right?
Thank you so much. This is fantastic. This is such an inspiring talk. I'll clap to everybody. Questions, comments, please.
I have a question. So you motivated the search for natural proof by you didn't want to have counting up to doubly exponential. But that can be then, you could have said that the proof should be of exponential length, or the proof should be in P space. Why not take a simpler definition of natural?
No, it's so no, it is not what we want to achieve. It's I view it as a test for what we are doing is right. It's sanity check. I view it only as a sanity check. It's not like it's not my purpose. But simply if your system, be it natural proofs or anything else, if it does not pass this check, then it means that it's, again, it's not what you're interested in. Okay. It's not the purpose. It's not the purpose. But it's excellent comment. Thank you.
Okay, thanks.
More questions?
I can ask a question.
Mm-hmm.
You ended with a comment about lifting versus natural proofs. So I was wondering if you think there's any connection between the two in the techniques or the approaches.
No. Let me, I think it's more, again, I had to revise, which means vandalize my large talk, put it here, right? So in the long version, it refers only to this result.
Okay.
So natural proofs, so it comes here in this business, or if you have a system with feasible interpolation, right? And you want a pseudo-random, natural pseudo-random generator, then you do very primitive lifting, extremely primitive. But still you do it. Is there anything like that for natural proofs or for other systems? It's very limited question.
Okay.
Sasha, so in this diagram that you have on the slides, so you were asking about the arrow on the bottom. Mm-hmm. So your proposal is to use these what Jan Krejcik calls tau formulas.
What formulas?
Tau formulas. These formulas saying that something is not in the image of a pseudo-random generator.
Yeah,
so this should be the arrow down.
It's one possibility. So and it's made.
Is it your conjecture or that this is the right arrow, or you suggest it as one possibility?
No, this conjecture is made in my annals paper. It's quite official.
Mm-hmm.
Or are you asking in the reverse direction? So if it
no,
is,
I'm asking whether this you propose this as the solution of what the arrow should be. So I know that you propose this conjecture, but do you propose this as the only solution of this arrow, or
well, this solution has extremely, maybe a bit dirty, but extremely powerful, something extremely powerful behind it. It might be bad, it might be totally incorrect, but we don't have anything else.
Mm-hmm.
At least I am not aware of anything that I would recognize as a project, as a plan to get it. I had tried lots of things.
Mm-hmm.
And it's very frustrating. You have an object, right, which is essentially a sequence of circuits, polynomial size circuits. Each one of these circuits computes one, because it's a tautology, and you want to get some computational content out of it, and you fail. I don't understand why. Even in 30 years, I guess, I still don't understand why we fail. So it is simply, it's like democracy. I would compare this to random generators with democracy. It may be a bad system, it might be a lousy system, but it's better than anything else.
I have a quick question. So you were talking about S12 as kind of the right system, the right power to talk about complexity. But in recent years, people have been working with systems that formalize probabilistic reasoning, APC1 and friends. What do you think about that?
It is, first of all, it is definitely a very interesting line of research. And I certainly don't want to say anything negative about it, but somehow I feel that, I mean this one, yeah? Somehow I don't feel quite strongly in terms of this thing. It looks like these systems, they, in many cases, they were somehow to formalize or capture particular things. It's not the case with bounded arithmetic, right? Bounded arithmetic was not invented to prove something or analyze proofs. It was invented to capture polynomial time. It's not with piano arithmetic, not the case with piano arithmetic. It was intended to capture all finite arguments. Somehow these systems, I'm not sure that they, whatever.
Well, thank you. Thank you so much. So more questions, comments?
Can you go back to the slide where you have this generator that you talk about?
What? I'm sorry.
The Nissan Wigderson generator, the first time that you talked about it.
No, it's not back. It's forward.
Yes, yeah, this one. So can you go back one slide? The one where you have the mapping from functions. Yeah, this one. What exactly? What exactly are you saying here? So I'm just trying to understand this.
So I'm saying that if you take any reasonable generator, for example, Nissan Wigderson, right? And I ask you a question, like I give you identically zero, or almost all strings here are not in the image of this generator. Yes?
Yeah.
If I am asking whether identically zero string is in the image of this generator or not, you will not be able to answer this question, regardless of any proof complexity. Just fix it in any reasonable way. Of course, you can always manually ensure that it is not there. But if you don't play any tricks, then you will not be able to answer this question about identically zero string.
Okay, thanks.
And we simply generalize it to all other strings.
Great. So thank you so much. This is fantastic.